Hello, everybody. Welcome to your physical geology lecture number. This isn't the right number. Let me fix that really quick. Hold on a second here. Number what? This is like 23. I don't know how that happened. It's okay. Lecture 23 for physical geology. We're starting volcanoes today. We're going to be doing another lecture of volcanoes next time, and then we're going to finish up with a lecture on geologic time. So then we'll be all done. So we're almost to the end, and I got my pen here, so we'll start taking a look at the slides. And oh gosh, you know what? I forgot to open up my lecture assignment too. I need lecture assignment number 23 here, volcanoes. Okay, and I'm going to put that over here so I can look at it while we do the lecture. So here we go. So what we're going to copy, what we're going to look at today are these subjects. Let me turn the pen on. Okay. How composition affects the eruptive style of the volcano, how the composition affects the lava viscosity, how composition affects the volcanic landform, that means like the shape of the volcano, what the volcano looks like, and the products of eruption, what actually comes out of a volcano, it's a lot more than lava, and also hazards. And so then next time when we talk about volcanoes, we're actually going to talk about historical volcanoes next lecture. They're actually like important volcanoes in human history. So anyway, you'll notice that composition comes a lot here. And what is composition? Just to be clear, because I realize a lot of people don't actually understand what composition means. It means like the chemical composition, like the what chemicals are in there, what elements of the periodic table, whether it's silicon or oxygen or aluminum or whatever it is. But whatever that elemental composition is, that's what we're talking about. Okay, so we're going to kind of start with the idea there's sort of like two main types of eruptions. Okay, and they're affected by the composition. So there are rather violent, large, you can see this woman running away from this huge eruption in Indonesia, and you can see the big clouds of ash rising up in the background. So there's these rather violent, explosive eruptions that send out big plumes of smoke and ash. And then there's ones that are relatively gentle, and I know that it doesn't look very gentle. You can see in the pictures burning down forests and stuff like that, but it is rather gentle in the sense that it's not blowing up. It's just effusing out and spreading lava over the ground. Okay, so remember that volcanoes are extrusive igneous rocks. Extrusive means that they extruded onto the ground. Okay, so there are extrusive igneous rocks, but remember that there are also kinds of igneous rocks that are not extrusive and not volcanic. Extrusive is another word for volcanic. So extrusive just equals volcanic. Okay? So those are extrusive rocks, but there's also these intrusive rocks. Those are those plutonic igneous rocks. Do you remember those? Plutonic igneous rocks. Plutonic igneous rocks form from a melt underground. So they never come to the surface and actually exude onto the surface. They form underground. So those are things like dikes, sills, plutons, magma bodies, anything like that. Those are plutonic rocks. Extrusive rocks, those are like the volcanoes, right? So we got these two kinds of igneous rocks that we're going to talk about, and these are sort of, for the most part, the mafic melts and the intermediate melts, and these are for the most part the two different composition of melts we'll talk about today. There are felsic melts, of course, but felsic melts are just very rare. So you'll see realistically in Earth that we have mostly mafic lavas and we have intermediate lavas. Okay, so but we'll talk more about those later. But right now, one thing I want you to be aware of is the kind of tectonic settings where we get. So this is number 3 on your lecture assignment. The kind of tectonic settings where we get mafic melts and where we mostly get intermediate melts. Okay, now this isn't like a hard fast rule that applies always. It's just generally true. Generally speaking, this is true. Okay, mid-ocean ridges, you'll get mafic melts. So at divergent settings, you usually get divergent tectonic settings. You usually get mafic melts like basalt. Okay. At subduction zones, you will get, which is a convergent setting, you usually get andesite. You will get some basalt as well, but there will be andesite. So it's usually like a mix of andesite and basalt. In continental divergent settings, rift zones, you can sometimes also get felsic melts. Okay, they're rare, but they do happen, and those are a lot of times, are associated with supervolcanoes. Okay, so and then there's also hot spots where you can get supervolcanoes as well, and you get felsic melts. But for number 3, tectonic setting of mafic lavas, put, for the most part, generally speaking, divergent settings. For intermediate, put convergent settings, especially subduction zones. Okay. All right, so that's what I wanted to show here. Remember that igneous rocks form from a melt. You have to have a melt, right? That's how they start off. They start off from lava or magma. Okay. Sorry, I needed a drink of water. Pardon me. But lava or magma. If it's an extrusive rock, a volcanic rock, it forms a lava, right? That's a lava. If it's intrusive, it's a magma. Okay. So anyway, moving along, composition determines the eruptive style, right? Composition, composition, composition. It's what we're going to be talking a lot about today. And what is the composition of mafic rocks, igneous rocks, right? Felsic, intermediate. What is the composition of those kinds of rocks? So remember that felsic is a combination of the word feldspar and silica. They are low in magnesium and iron. They are high in silica. They're also high in sodium and potassium. Okay. The kind of minerals that are present are feldspar and silica, which is quartz. Okay. So those are the kind of minerals that are very present in felsic melts. Mafic. Mafic stands for magnesium and ferric. Okay. Which is iron. It's Latin for iron. So magnesium and iron are rich in the mafic melts. They are low in silica. Okay. In between, we have intermediate, which is just, medium in the amount of silica. And the minerals that are present are especially things like plagioclase. Okay, sometimes amphibole. Things like that. Now, what minerals are present in mafic? We get pyroxene, olivine, and plagioclase. Okay, so that's what you want to put for number 2. Rock names. We're looking at the extrusive rocks. Okay, so we're right up here. Felsic is rhyolite. Andesite is intermediate. Mafic is basalt. There is an ultramafic one called komatiite. It's extremely rare, and it isn't formed in the present day. It was only formed in ancient times, in the Hadean, billions of years ago. Okay, Earth has cooled down too much to allow that kind of rock to form. All right, remember Bowen's reaction series way back near the beginning of the class, okay? So the first minerals to crystallize at the hottest melts are olivine, then going down to pyroxene. That gives you, of course, the mafic type rocks. They're cooling from very hot magma. As things begin to cool, we get amphibole, mica, potassium, feldspar. They all start to be precipitated out. Okay. Finally, when you get down to felsic, you get potassium, feldspar, muscovite, mica, and quartz. Okay, so the felsic type things are down here. Intermediate is over here, and the mafic is up here. That is the, of course, famous discontinuous Bowen's reaction series, right? On the flip side, we have the continuous one. We already learned this a long time ago, so this is review. At high temperatures, we get calcium-rich plagioclase. These are all the plagioclases, right? Coming out of the continuous series, continuous Bowen's reaction series. Starts off calcium-rich with calcium-rich plagioclase, and eventually becomes more sodium-rich as we go down to felsic. Plagioclase is in almost everything. If I ever ask you what mineral is in X rock or Y rock or Z rock, if you guess plagioclase, you're probably right. All right, so let's move along to effusive eruptions and explosive eruptions, okay? So the kind of lavas that sometimes you see in places like Hawaii, you might notice that Hawaii is composed of this black rock. Guess what that is? It's basalt, right? Basalt's that famous black rock, and that is a mafic rock. And you've probably seen pictures of Hawaii with these flowing orange glowing rivers of lava, going like just like a river, right? A river of fire going down the basalt. And the question is, what's the composition of that? It's mafic. Okay, so those are mafic basaltic compositions. Okay, they are very fluidic. And their eruption style is very effusive. So no big explosions here. They don't go off with a bang. They just effuse out. Okay, and the reason for that is because they are not very viscous and they don't hold very much water in them. Okay, we'll talk more about that later. On the flip side, what do we have? We have eruptions that are explosive from felsic or intermediate. Okay, I could also write here intermediate. Intermediate eruptions and felsic eruptions. That's the composition. What is the composition like? If it's felsic or intermediate, you're talking about a more explosive eruption. Think of Mount St. Helens. That was one of the biggest explosive eruptions in U.S. history, if not the biggest explosive eruption in U.S. history. Okay, on U.S. soil, I mean, of course. Mount St. Helens, it was an explosive eruption that spread ash for miles and miles, even all the way down into Texas. There was ash from the Mount St. Helens eruption, which took place in Washington State. Okay, these are big bangs, big explosions. Okay, that's not like Hawaii. Hawaii are these effusive rivers of lava. These are explosive. Okay, and those are erupting intermediate style magmas. Those are andesites, things like andesite. Okay. Now, I want you to think a little bit about this. Why is one explosive and the other one is effusive? Why is one explosive and the other one's effusive? So there are a few reasons for this here. The main difference, though, most important factor has to do with viscosity. So mafic style lavas, they are not very viscous. They are more fluidic. And that has to do, actually, with the silicate interconnectedness. I think I told you a long time that silicate interconnectedness touches on almost everything. And it touches including here when we talk about volcanoes. So here at Hawaii, we get these effusive mafic style volcanoes. They have very little water, almost no water. Okay, and the water, think of water as like steam power. You know how they have like steam engines and things like that? Volcanoes are powered in a way by the water, almost like a steam engine. The more water it has, the more explosive it is. Because you know what water is like, hot water under pressure. It's dangerous, right? It's explosive. Think of a pressure cooker, ready to blow, right? It's very, very dangerous. Hawaiian type lavas, mafic lavas, have almost no water. And the water that they do have can easily exsolve out and escape the lava because the lava is not very viscous. More viscous materials, they can hold their water better. And so places like subduction arcs, where you have very viscous intermediate style lavas, are going to hold their water better. So there's going to be a lot more water dissolved in the lava. Hawaiian lavas only have about 0.5% water. These lavas over here at subduction zones have 4 to 5% water. That's a lot. And you have to remember that we're talking about water, 4 to 5% weight percent. That's a lot. Because remember, water weighs so much less than the lava. It's much less dense than the lava. So to have 4 to 5% weight percent, It's a lot. Okay, so there's a lot of water in these lavas. The water is trapped by the viscosity. It's high-powered steam ready to blow, and when it finally gets a trigger, it blows and it explodes, right? So there's a catastrophic release of the vapors, of the gases, mostly water, but there's other stuff, gases into the atmosphere. And that's what powers the explosive nature of these volcanoes, okay? So anyway, based on what you know about how melts are produced at mid-ocean ridges versus subduction arcs, what setting do you think are going to produce melts with more water? Subduction zones are going to produce melts with more water. Why? Because, and a lot of people want to put mid-ocean ridge here because they think, oh, mid-ocean ridge, it's in the middle of the ocean, there'll be more water. No, it's because, remember, mid-ocean ridge lavas form from decompressional melting of the mantle. Subduction zone lavas form from flux melting of the mantle. Flux melting. What is the flux? What's the thing that's lowering the melting temperature? It's water. There's a lot of water in those melts and in those lavas, and that's what powers the explosivity. So high temperature, low viscosity, effusive lava flow at Hawaii. It forms this beautiful ropey texture you can see here. We actually have a fun word for that. It's a Hawaiian word called pahoihoi. So that's what that ropey kind of taffy-looking texture is right there. So there's beautiful. Ooh, doesn't that look nice? That pahoihoi. Doesn't that looks so attractive, even though it's red-hot lava. There's another kind of lava that is actually much kind of like spikier, and it's called a'a. And they call it a'a because that's the sound that it's a Hawaiian word, and it's the sound that you would make as you walk over the spiky, sharp lava. So, and of course, I don't mean when it's hot. I mean when it's cooled down, right? So even though it seems weird to say it, this is actually a gentle volcanic eruption, but this is what an effusive Hawaiian-style eruption looks like. So high temperature, low viscosity, effusive lava flows on Hawaii. There it goes. Rushing into like a red river of fire, rushing into the water and cooling down, right? So it gives you a pretty good idea of what these lavas are like. You can see. I know it looks pretty viscous, right? It looks, but that's actually very low viscosity for a lava. When these kinds of things, by the way, just FYI, when basalt cools underwater like this, it forms these things called pillow basalts, and they call them pillow basalts because they look like pillows. So we can actually find 480. This is actually pretty cool. Pillow basalts is one of the ways that we know when there were oceans on Earth's surface, because we can actually find the earliest point we find pillow basalts is 480. We have ones that are even older than way older than that. Actually, that's relatively young, but it's one of the ways that we know when there were oceans on Earth is by the presence of pillow basalt. So this is showing a little movie showing how pillow basalts form underwater from underwater magmatism. So anyway, those are your effusive lava flows, relatively gentle mafic lava flows. The opposite of that are intermediate and felsic type lavas. These are andesitic, intermediate, or rhyolitic. That's felsic. Okay, felsic are a lot worse than andesitic ones. They're just devastating supervolcanoes, actually, is what they are. These have high gas pressure, and it is the high gas pressure. It's able to maintain that high gas pressure because it's so viscous. The viscosity of that lava, it's able, the gas bubbles get trapped in there, basically. Is what I can tell you. It's very Si rich, okay? That means rich in silica, okay? I'm going to show you a little something just to kind of give you an idea of how viscous lavas trap gas. So just wait a second here. Okay, so now I should be big, and now you can see me on the big screen here. So what I got for you, two things. First, I have a beaker of water. Okay, there's the water. And then I have a beaker full of slime. Okay, so there's the slime. So which is more viscous? Ask yourself that. Which is more viscous? If you're thinking to yourself it's the slime, then you're right. The slime flows very slowly, right? If I did that with the water, all the water would pour out into my lap. But when I have the slime, it pours out very slowly, right? So it doesn't flow easily, and that means you're more viscous. So imagine that this is the intermediate style lava, and so this is the intermediate style lava, and this is the mafic style lava. Maybe that's not such a good angle, but what I have here is just some pressurized gas, right? It's just pressurized air that people use to. I've shown you this a lot, but you clean your keyboard with it, and I use it a lot in my little demonstrations here, though. But you all know that if I put this in the water, and gosh, I hope I don't make a huge mess. Oh, there it goes, just a little bit of bubbles, right? And I'm not going to put this over my laptop, but what happens if I release some of the gas? It just quickly escapes. Do you notice how the gas, right? It's gone. It's escaped. Is that going to happen for the slime? Let's see if I put some in here. Okay, I'm going to put some in here, and what happens? Well, besides it makes kind of a horrible fart noise. But actually, what you'll find is that it's much easier for it, and I hope you can see a little bit, but can you see how the air bubbles are trapped in there? Do y'all see that now? So they're actually air bubbles trapped, right? If I did it more, I could really trap a lot of air in there, okay? So you can see at the bottom there's now air trapped in there. So why does the air get trapped? It gets trapped because it's more viscous, okay? So that's the point. It's the same thing with intermediate style lavas. They trap the gases. So I'm going to turn this on to the slideshow. Okay, there. Now you should see a slideshow. And what was I getting at? So it's the fact that those intermediate lavas are so viscous, they trap the gas, that gas pressure can build and then kabooey. Whereas with effusive lavas, they're so fluidic, the gas just escapes easily. Okay? So that's one of the main reasons that there's a difference in the explosive style. So pressure is released in a catastrophic way. Okay? Pressure is released in a catastrophic way. So kaboom, right? That's how intermediate style volcanoes go. They're catastrophic releases of gas. Here's another just dramatic picture of a Sinabung volcano in Indonesia. Okay, another very just historically. We'll talk actually more about this one in the next lecture, so I don't want to talk too much about this. But of course, there was the very famous eruption of Mount Vesuvius that destroyed Pompeii. That's in 79 AD. And what's pretty cool is that we actually have drawings of what Mount Vesuvius looked like prior to the eruption. And I mean, look at this. I mean, this is crazy. That's how much mass was blown off of the top of that rock. I mean, can you imagine? You're literally talking about a mountain flipping its lid, blowing its lid. And that's what's happened. That much gas pressure. Imagine the amount of gas and heat and pressure needed to blow the top off of a mountain. Okay. One kind of eruption that you get in places that really have a lot of water are called phreatic eruptions. So these are eruptions involving kind of underwater explosive eruptions. Okay, so these are intermediate style eruptions that happen underwater, and they involve a lot of a lot of water being released. So submarine, shallow, steam-driven explosions can create phreatic eruptions. Okay, so we asked what are eruptions of mafic lava like compared to intermediate? How does the viscosity of mafic lava compare to that of felsic? We already answered that. Oh yeah, so we're kind of like on number 8 right now. Okay, what volcanic structures are produced by mafic lava compared to intermediate? Okay, some more famous phreatic eruptions. This is Krakatoa. Again, I'm going to talk about these eruptions later in the next lecture, but Krakatoa is, in human history, like recorded history, the biggest eruption we've ever experienced, and it completely destroyed the edifice of this volcano. You can see it's totally leveled to the ground. The sound of this volcano was heard thousands of miles away. People that were close to it, if they weren't killed by the tsunami or killed by the explosion, went deaf just from their eardrums, being blown out from the sound of this thing. It was such a massive eruption. So anyway, a little bit about viscosity here, a little bit more about viscosity. It's how things flow, right? So water is not very viscous. Oil is maybe somewhat viscous, and peanut butter is very viscous. Okay, so Felsic is. This is actually a really good slide, by the way. You should know everything on this slide. It really summarizes things up for you in a very good way. Felsic are more viscous. Mafic is more fluidic. But also, here's like the silica content. Here's the sodium potassium content, the iron magnesium calcium content, the temperature when they start to melt. A lot of good stuff shown on that slide. Just to give you an idea of kind of viscosity of some everyday things, water has by definition a viscosity of 1. If you're wondering 1 what? It's 1 Pascal second. Of course. Doesn't matter. It is a Pascal second. That's how we measure or quantify viscosity, but you don't need to know that. But it has a viscosity of 1. Maple syrup has a viscosity of 2,000. Peanut butter has a viscosity of 250,000. A typical Hawaiian basalt has a viscosity of between maple syrup and peanut butter. Andesite has a viscosity many times greater, significantly many times greater than peanut butter. Okay, so these are really viscous things. Anyway, I think we've talked a lot of this stuff. Let's go on to landforms. So I want to show you just 2 main landforms that you should know. One is this stratovolcano, and the other is a shield volcano. And one thing I just want to point out is that this has very steep sides. It's kind of more what you like stereotypically think of as a volcano. You know, it's got steep sides. It's very high. It's like so think of things like Mount Fuji, Mount Kilimanjaro, places like that. Those are stratovolcanoes. Shield volcanoes are very low relief. They kind of look unremarkable. They look like maybe just big hills, you know. But one is produced by one kind of volcanic eruption, the other is produced by another. So shield volcanoes are, again, very broad, very mild, very low relief. That means low to the ground, and they don't stick out very much, low topography. They are formed by mafic lava that spreads out all over all over the place, right? So it just spreads. So you know that if I took, again, my water, this is like my mafic lava, and I'm not going to do this, but if I poured it out on my desk, you know, what would happen? It's going to spread everywhere, right? It'll spread all over my desk. Whereas if I take my slime here and I pour it on my desk, you know, whoa, comes out in one thing. It doesn't spread out everywhere. I mean, it spreads out slowly, but imagine if it was a lava trying to cool, it wouldn't have time to spread out. So anyway, I'm going to put my slime back before I get into trouble. But anyway, viscous lavas, like intermediate style lavas, they move more slowly so they can kind of build up more of an edifice, okay? So these composite or stratovolcanoes, aka stratovolcanoes, form steep sides and these steep, sharp, triangular type peaks. So what do you think of that guy? What do you think that is? If you're guessing a shield volcano, you would be correct. Okay, and they look pretty unremarkable, right? They just look like, it looks like a hill, you know, kind of a shallow hill. And so that's how they are. Whereas if you go to Alaska, which is a subduction zone on the Aleutian Islands, you find Pavlov and Pavlov's sisters, which are composite volcanoes. They're stratovolcanoes. And they're very sharp, steep sides. Okay. Other kind of edifices you sometimes can encounter are things called obsidian domes or glass domes. These are really steep-sided domes that form from oozing felsic melts. Okay, and they actually form obsidian, right, which are really, really useful material for Native Americans, right? It was highly traded material because you could make it into arrowheads and spearheads or whatever. Okay. So those are kind of 3 kinds of volcanic edifices you should be familiar with. Okay, composite stratovolcanoes, composite volcanoes / aka stratovolcanoes, shield volcanoes, which are mafic, and then obsidian domes. Okay, so moving right along, volcanic products. What comes out of a volcano? So I'm sure you all know one thing that comes out of a volcano is lava. Okay, that's obvious. You learning that probably since you were little kids. Okay, but so we do have flows. So basaltic lava flows are more dangerous than andesitic lava flows because basaltic lava flows are much less viscous, so they can flow. They're fluidic, so they can flow into these rivers, and they can go very long distances, sometimes 10 to 100 kilometers. And they can move as fast as 30 kilometers per hour. So that's pretty fast. This is just a really cool picture. So you can see that this lava river is flowing, but it's formed kind of a crust on top of it. You see that? So it's flowing, but it has a crust on top that's cooled down because it's in contact with the air. But the river underneath is still flowing. So after these rivers of lava crust over on top, then the lava drains out to some low area, wherever it is. You end up with these tubes. So if you ever want to go exploring lava tubes without having to fly to Hawaii, you can go to Craters of the Moon, Idaho, and there's actually all these cool like lava tube caves that you can explore around in. It's a really neat place. On the other hand, you have viscous flows from like andesite, and you can see that these flows of lava, they only make it down, like that's how far they make it down. They don't even get all the way down the side of the mountain before they freeze because they just move too slowly. So these things are going like just inch by inch. They just go very, very slow. This video is private. Can't even remember what I used to have there, but I thought I used to have an eruption. But anyway, what can you do? Last thing are lava domes. So lava domes, these are felsic compositions. They often plug the vents and allow pressure to build up till there is an explosion. And that's how you get these lava domes right here. So, all right, so lava, that's the first thing, a lava flow. Another thing that you might know about are the erupted fragments. Erupted fragments are all the little rocks that get thrown out of the volcano. So that could be anything from volcanic ash. And volcanic ash, by the way, it is just little particles. It's like, think of like rock flour, like pulverized rock. So that's what it is. Just pulverized rock. And that's been generated from the explosion. Like I said, they found volcanic ash all the way down in, Texas. I'll show you the picture. It's pretty crazy. Or maybe I don't have it right here, but all sorts of things, all the way down to Oklahoma and Texas. They found this, and it erupted. Mount St. Helens erupted in Washington State. Lapilli are things that are kind of walnut sized or nut sized. They're little rocks, pebble sized, kind of things like that. And then bombs and blocks are things that are big. They're like beyond 64 millimeters, so that's like bigger than your hand. We call that a bomb or a block. And they could be really big. Some of them could be really big indeed. There's a guy standing next to you could see it. I guess it's up there. But you could see this guy standing next to a big block or bomb, right? So anyway, another thing that comes out of volcanoes are gases. Okay, so gases also emitted, and the gases actually can be all sorts of things. Most of it is water. Okay, most of it is water. However, I'm trying to see if I ask you, it would be a good question to ask you what's actually the composition of the gases, but I guess I don't ask you that on here. But most of it's water. That's the most abundant gas to come out of a volcano, like I keep saying. Carbon dioxide is also there, and sulfur dioxide is also there. So you know that a lot of times sulfur gets emitted around volcanic vents. The CO2 can actually be extremely dangerous. Sometimes the CO2 gas from a volcano travels down in a big blob. And it's, of course, invisible. You can't see it, but the volcanic gas, carbon dioxide gas, travels down into a valley and gets trapped in the valley, and it suffocates anybody who's in the valley or any cattle that are there. Very, very dangerous. In Mammoth, California, where there's an active volcano, they actually have CO2 warning sensors that for the whole city, because if there's too much CO2 gas being emitted by the volcano, the sensors will go off to warn people that, and it happens sometimes. There could be CO2 leakage that goes on from the volcano. It can suffocate, kill people. Okay, talking about hazards now. Hazards are kind of linked to the stuff that comes out of volcano, right? So the flows can, of course, be very hazardous, right? Most people don't get actually like a flow doesn't actually kill them. I don't know of anybody ever dying from a lava flow, but it can definitely destroy your property, right? This is kind of a funny video. I guess I shouldn't call it funny, but it was kind of funny to watch this Ford Mustang get eaten up by a lava flow. But anyway, this is in Hawaii, so there comes the lava, and lava doesn't care about your car or your road or whatever else. So there it goes, getting engulfed in lava. It looks like it's actually kind of funny because you can see they sped this video up quite a bit, so it's actually moving a lot more quickly than this. Or I'm sorry, much more slowly than this. So bye-bye to your Ford Mustang. There it is, pushing up against the grate. And it's going to just bust through that fence right there. It's pretty interesting to watch. There was recently a big volcano in La Palma, which are in the Canary Islands off the west coast of Africa. It had a lot of really cool footage, a lot of dramatic footage, and this is one of the first volcanoes in La Palma that they've had drones, so they really made a lot of great videos, drone footage of that volcano. Like I said, gas emissions, very, very dangerous. Sometimes gas can be released, but one of the dangerous things that can happen is the gas is emitted from the volcano underwater, and then it releases catastrophically. And like I said, it can kill cattle, can kill people. Another thing that can happen is actually happen too that's kind of related to the gas release. Maybe you could consider this a separate hazard, but climate change. The climate can be, for a short time, altered by volcanic eruptions. In fact, some of the biggest mass extinctions on Earth, we think, actually the biggest mass extinction on Earth, we think was it happened because of massive climate change. It was short-term climate change, but still massive climate change from a massive volcanic eruption or series of eruptions. So a good example of this was Laki, Iceland, 1783, which is right, when our country was getting started. And it wiped out, take a look at this, it's an 8-month-long eruption. A lot of material was emitted, 12 cubic kilometers. That's a lot. Mount St. Helens released 1 cubic kilometer of material. This released 12, so 12 times the size of Mount St. Helens. It released a lot of sulfuric acid, and what that does is it acts as an albedo. It increases the albedo of Earth, and it deflects, it's an aerosol, and it deflects light back into outer space, so it lowers temperatures. So it caused a complete crop failure in Iceland, caused acid rain. It also wiped out 25% of the population, 80% of the cattle, and it lowered temperatures in even all over the world, even in the United States. So there was kind of a mini ice age that resulted from this volcanic eruption. Ash is very, very dangerous. Very dangerous for airlines. You know that if you get ash into the engines, it can actually shut down the engines, destroy the engines, and have total engine failure. This was kind of took people off guard. I think that they, in the earlier days, they didn't understand how dangerous the ash plumes were. And there was this very famous KLM flight, which I'll play it for you here. Got caught in a ash flow. I don't know if you can really hear this, but
Heavy, Roger,
Well, it's pretty frightening, right? So, anyway, but this shows what happens when an airliner flies into an ash plume. Very, very dangerous. Let me get my PowerPoint back up here. And I don't know, probably some of you might remember this, but they had all of these volcanic eruptions not too long ago in oh man, I can never remember how to say this. Eyjafjallajökull. It's Icelandic. I'm sorry. There's a.
Eyjafjallajökull.
It's hard to understand. It's Icelandic place, but it was in Iceland. It wasn't too long ago. I think it was maybe in like 2014 or 2013, something around there. Maybe 2015. But it like totally shut down flights out of Europe because it was impossible to get out of Europe because of the ash in the air, and it destroys the engines, the airline engines. Is what I'm trying to say. Pyroclastic flows are really one of the most dangerous things. Really terrifying.
Something triggers a pyroclastic flow about 10 times bigger than all that came before. Within moments, it overwhelms the valley.
So the flows of ash, hot ash, they're like 600 degrees Celsius ash. Very, very dangerous. Pretty terrifying, right? It's imagine that thing coming at you. So luckily, this was recorded on a closed circuit security camera. But anyway, oh by the way, if you're wondering what's happened to that 747 KLM flight, they did actually land safely. Okay, so they landed safely in Anchorage. Another thing that's extremely dangerous are lahars. By the way, this is kind of going in order of danger. So lahars are very dangerous as well. Lahars are, you might be wondering, what is a lahar? A lahar is when it comes after the eruption, and it's when you have may rain or ice melt, and it mobilizes all of the ash. And maybe there's just tons and tons of ash that has been emitted by this volcano, and it gets mobilized by water. There's no plant roots or anything to kind of slow it down or stop it or keep it together. It's totally unconsolidated, loose ash. Gets mobilized by the rain and picked up, and it's just devastating, devastating like mud flows. Terrifying and devastating. Actually, more people died in the lahar from Mount St. Helens than actually died in the pyroclastic flows or the eruption. So they're very... This one in Nevado del Ruiz in 1985 killed 23,000 people. And was it in Colombia? Yeah, it was in Colombia. So very, very dangerous. And they move very fast. 40 miles per hour, these things can move, right? So there's Mount St. Helens. The lahar from Mount St. Helens killed more people than the flow. So this is Mount St. Helens before the eruption, and that was it after the eruption. Isn't that amazing? Amazing. Thing just blew its top, right? I'm not going to play these, but there's a lot of just great movies here about the Mount St. Helens eruption, if you want a little bit more background. But it lost 1,300 feet. Isn't that crazy? It used to be a pretty tall mountain, and then it got 1,300 feet shorter. Amazing amount of energy that blew the top of that. Okay. So anyway, there's the Mount St. Helens, more on the Mount St. Helens eruption. This is the map I wanted to show you. This is the ash, you can see ash, I guess none in Texas, but in Oklahoma there was even ash from the Mount St. Helens eruption. So you could see all the trees got blown down. You could see the tremendous loss of material off the top of Mount St. Helens. So there you go. That's what it looked like. This is the view from Spirit Lake, 1969 compared to 1982. So just tremendous. So we'll talk more about Mount St. Helens next time. This is what it looks like now, though. Last thing I want to talk about in terms of hazards are tsunamis. Tsunamis are generated when there's all this material you can imagine gets blown off the volcano and it falls in the water, and it can create a huge tsunami wave, right? So it can generate a wave like that. One thing that could actually threaten the east coast of America is if there was a volcano on La Palma, which there was, just like as I'm speaking, that's about a year ago. So that did not happen to create a tsunami, but there could be if there's a big enough eruption on La Palma, it could generate a tsunami that could affect the east coast of our country. So we are not immune from that. So here's some just great footage. 2021 eruption of La Palma. So this is just last year. And like I said, this is like one of the first big eruptions where they actually had drones, a lot of drones. So they had a lot of drone footage. And they have these great images of like the lava flowing into people's swimming pools and things like that. So pretty crazy places. Pretty crazy videos. So there it is, the lava falling in and starting to boil the swimming pool like a big bowl of soup. So yeah, but anyway, I don't know how much of this you want to see, but you can see the big white steam coming up out of the pool as the lava flows into the pool. It's crazy. Okay, well, I think I covered everything. So anyway, you can look that up on your own, I guess. But I hope you enjoyed the lecture. So we'll continue next time when we talk about kind of historical volcanoes and go into all the different historical volcanoes that have been important in all over the world. So anyway, we'll talk about that next time, and then we'll have just 2 more lectures left. So have a good weekend and have a good week, and we'll see you next time.